So what else can you do with quantum entanglement? Here's another cool protocol that I'm going to describe very briefly for you, and it's called quantum teleportation. So imagine the following situation, that Alice and Bob, the two heroes of the story, are miles away from each other. And they do share entangled state, say in state omega. So that is this maximally entangled state, 1 over square root of 2, 0, 0, plus 1, 1. So the two qubits are entangled in state omega, and at some point someone comes to Alice with a state psi. Alice has no idea what the state psi is, and but she would like Bob to get the state. But let's assume that for some reason it's impossible to send the qubit as it is from Alice to Bob. So is there any other way she can transfer the state from her location to Bob's location? So here we come with quantum teleportation. So essentially what Alice is going to do is to take this qubit, combine with a qubit that is entangled with Bob's qubit. She's going to perform a certain measurement on the joint measurement on two qubits. We call it a measurement in Bell basis, or the Bell measurement. Remember, I was telling you about the Bell state that form orthonormal bases in the four-dimensional Hilbert space. So the two qubits, mathematically speaking, live in this tensor product of Hilbert spaces pertaining to each individual qubit. So altogether, it's a four-dimensional Hilbert space which has this tensor product structure. So now the measurement in the Bell basis will give you 4 possible outcomes, and then Alice is going to communicate the outcome of the measurement to Bob. So assume that there is no way to send a quantum bit, but she can send classical bits over some kind of a classical broadcasting channel. And Bob, upon receiving this information, is going to apply a certain unitary operation to this qubit that he holds, and the outcome of the whole thing will be state psi. So there's a little bit of a magic going here, but let's try to demystify, make it more mystical, demystify, whatever. So so let's first of all look at, let's number those qubits. So that's qubit number 1, qubit number 2, qubit number 3. So the state of the 3 qubits is essentially this. So this is my unknown quantum state psi. Call it alpha 0 plus beta 1. And this is the state omega. So this is the Bell state, one of the Bell states, and describing the 2 qubits that Alice and Bob share. Now, there is just a brute force algebra, if you wish, that allows you to decompose, to write it in a slightly different way. So do a little bit of calculations, and you can see that essentially you can represent this state, the same state, in the following form. But let's look carefully how we shifted coefficients from the first qubit to the third qubit. So as you can see, the first 2 qubits here are in the Bell state. So we have a superposition of 4 terms, and in the first term, the first two qubits are in the state, one of the Bell states, omega. This is another Bell state. This is yet another Bell state, and this is yet another Bell state. And then the third qubit then is in a state, well, in the first term here, it's in state psi, sort of some unitary modification of the state psi. So now, if Alice can perform this Bell measurement, she will, again, using this sort of ugly language of quantum collapse, she will collapse the superposition into one of the 4 terms. So if she is sort of collapsing it on the, if the outcome of the measurements is state omega on the 2 qubits, then she knows that the third qubit is in original state psi. So there's no need to do anything. So at this point, we do nothing to the third qubit. In this case, we have to, if you look at the third qubit, if this is the outcome of the Bell measurement, then you have to apply the sigma z or z operation to the third qubit just to recover the original state, right? Because the z operation will just simply flip this sign here. So it's the and we are done. So if this is the outcome, then as you can see, we have to apply bit flip operation to the third qubit. And in the last case, if this is the outcome of the Bell measurement, then we have to apply both phase flip and bit flip. So let's write it as x, z. So essentially the way the protocol works, so here's another explanation how it works in terms of a circuit, which may actually help you to understand it a little bit better. So in this case, the first 2 qubits, so again, this is my qubit 1, my qubit 2, and the qubit 3. So the first 2 qubits are on the Alice side, and the bottom one is on Bob's side, right? You may ask a question, okay, how do we perform the Bell measurement? I tacitly assumed that it can be done, but I didn't tell you how to do that. And it's not an entirely trivial question, but in a way you can work out how to do it. Remember how we generated Bell states? We used a circuit which looked like this. It was Hadamard and control not. And then we said that if we just put here 0, 0, that we get state omega. If we just put 0, 1, or 1, 0, or 1, 1, as the inputs will generate the 4 Bell states on the output. So there's this one-to-one correspondence between the tensor product basis and the Bell basis. So they are related by a unitary transformation. So as long as we can just revert this unitary transformation, so instead of projecting them on the Bell states, effectively we can actually reduce the projection on the Bell states to the projections on the computational basis. So for that, it's just enough just to reverse, to do the mirror image of this circuit. So essentially, Alice is going to apply the control not and the Hadamard. So that's compensating unitary transformation, and then we'll perform bit by bit measurement on the 2 qubits. And if the outcome is 0, 0, then she will just communicate, 2 bits of classical information, say, Bob, 0, 0, and Bob says, okay, fine, then I do nothing, then I have the state. And then if Alice says, well, 1, 0, so then Bob says, okay, 1, 0, then that corresponds into this situation. I apply Z phase flip, I recover the state. And then if it is 0, 1, then Bob applies X. And if it is 1, 1, the Bob will apply X, Z. So in general, we can say that Alice is shouting, okay, those 2 bits of information, A and B. And Bob will be applying here X, B, Z, A to the qubit to recover the state. So the state appears here. So it's an interesting thing. One thing you have to remember here is that remember we are talking that it's not possible to clone a quantum state, and here we are not cloning it because the original during the Bell measurement is destroyed, right? So in order to teleport from one location to another, we have to destroy the original. Otherwise, we would be cloning, and we know that quantum cloning is not possible